All right, team, how are we doing? I'm gonna have to straight up level with you. This set of notes was hard for me. So I actually have all the problems done. I'm gonna try to repeat them, but if I make some mistakes, it might happen. We'll compare it. I'm actually gonna upload the ones that I did beforehand as the official notes, but I'm still gonna work through them, try to see. It'll be fun, okay? All right, so here we're dealing with analytic coefficients, okay? So when we're dealing with analytic coefficients, that's things like we have this e to the x here, okay? So the first thing we're gonna do, we're gonna remember that e to the x has its own Taylor series, or Recursion series, power series. They're all pretty much mean the same thing in this context. So e to the x is 1 plus x squared. Oh, it's already making mistakes. 2 factorial x squared. So that's equal to the sum. Let's say n goes from 0 to infinity. 1 over n factorial x to the n. And just for our own sort of sake, I'm going to write this as the sum. N goes from 0 to infinity. B sub n x to the n, where bn equals 1 over n factorial. You'll see why I'm doing that in a minute, okay? So now let's start taking our y prime and y as we normally do. So y of x, we assume that it has its own power series expansion and goes from 0 to infinity. A sub n x to the n, y prime of x equals the sum, n goes from 0 to infinity, n a sub n x to the n minus 1, which by now we are experts at writing this. N goes from 0 to infinity. Shift it right, shift it back. We remember that our first term that's non-zero is when n equals 1. So we're going to need to shift this to n plus 1, a sub n plus 1, x to the n. Okay. Now let's go ahead and plug this in to the differential equation, okay? So, okay, y prime is now sum, n goes from 0 to infinity, n plus 1, a sub n plus 1, x to the n, minus, I'm going to write e to the x, but I'm going to write it in terms of its series, and I'm going to use the b sub n term. Okay, I'm going to use this form. I know what b sub n is, but we're going to use it that way. Oh man, I'm in danger of explaining this so well that I'm going to have to use this version on my notes, because I didn't think to do this b sub n before. But you'll see why I do that. So that's our e to the x, remember? And here's our y. Okay, now our y of 0 equals 1. Remember, that tells us that a sub 0 is 1, right? That's what this initial condition tells us. Okay, now we have to remember about multiplying power series together. Okay, well, we'll do that on the next step. So when we multiply power series together, remember this is going to be n goes from 0 to infinity, sum k goes from 0 to n, b sub k, a sub n minus k, x to the n. Okay, do you remember that? So I explain it, I think, in the 8.2 notes. Okay, I explained that. All right. So once you do that, n goes from 0 to infinity, n plus 1, a sub n plus 1, x to the n, minus sum n goes from 0 to infinity, k goes from 0 to n. Now I'm going to replace now by b sub k. My b sub k is 1 over k factorial. So now I'm going to get 1 over k factorial, a sub n minus k, x to the n equals 0. Okay, and now I'm ready to write my recursion relation. Okay, so my recursion relation is a sub n plus 1 equals 1 over n plus 1. The sum k goes from 0 to n, 1 over k factorial, a sub n minus k. All right, because remember, when we do the recursion relation, all we're doing is we're taking the coefficients of x to the n should all equal 0. Okay, so that's setting this plus this piece all equal to 0. Okay, and that leaves us with this. Okay, now let's go ahead and calculate a couple of these. Okay, so a sub 0 is 1. Okay, let's do n equals 1. Oh, sorry, n equals 0 is going to give us a sub 1. A sub 1 is going to be 1 times 1 times 1 over 0. That's going to be 1. So a sub 1 is going to be 1. Okay, let's do n equals 1. That's going to give us a sub 2. Okay, so a sub 2 is going to be 1/2 times the sum, k goes from 0 to 1, 1 over k factorial, a sub n minus k equals 1/2. Now, k equals 0. When k equals 0, we're going to get 1 times a sub 1 plus k equals, let me write that down, k equals 0 plus the k equals 1 term, 1 times a sub 0. A2 equals 1. Okay, let's do n equals 2. That's going to be a sub 3. A sub 3 is going to be 1 over 3. K goes from 0 to 2. 1 over k factorial. A sub n minus k, so that's 1/3. K equals 0 is going to be a sub 2 plus k equals 1 is going to be 1 times a sub 1. And k equals 2 is going to be 1/2, or 1 over 2 factorial, a sub 0. 1, a sub 1 is 1, and a sub 0 is 1. So that's going to be 1/3, 1 plus 1 plus 1/2. That's going to be what? 2.5, 5/2. Times 1/3, that's 5/6. Okay, so let's leave it there for now. We'll come back to this, don't worry. But if I were to do up to 3, then my basic solution is y of x equals approximately 1 plus 1 times x, that's the a1x, plus 1 times x squared, plus 5, 6x cubed. And I could keep going. Let me just check and see that's what I got yesterday. Yep, I had one more term yesterday. Okay, but I'm going to show you guys even better. We can, now it may be harder, but we can actually do some of this work with Sage, of course. Okay, so let me show you guys how that works out for us. So let me share my screen. There we go. Okay, so we're gonna go. I want to make sure that I'm seeing what I want to see. Okay, so we're gonna go ahead and 8.4 problems. Okay, give my computer a second, it's old. Let's zoom in a little bit. And this, zoom back out a little bit. This is the problem that we're doing really. Okay, so here's the sort of the loop that I did. So I started, I set a vector. Oh, okay, I started by saying how far I wanted to go. I wanted to go out to 10. I could go out as far as I want now. Shall I go to 100? That might be exaggeration, but I could, right? Let's see what happens when I do that. Okay. I make a list of vectors. They're all zeros. These are my a's. I start out with a0 equals 1. I define a variable because I'm going to write out the polynomial as well. Okay. My t is a sub 0, no problem. Now I'm going to do the recursion. Okay, so for basically I'm going to run through my list in my vector. I'm going to run through the vector. Okay, and here's where I do it. So this is that part. This part here is just that little part that's the sum. K goes from 0 to n of a sub n minus k times 1 over k factorial. I mean, it's literally what it is, right? A sub n minus k times factorial of k, okay, times 1 over factorial of k, all right? This is the part where I take a sub n plus 1 equals 1 over n plus 1 times s. So let me real quick show you guys again what that, you know what I mean. I want to show you real quick what the recursion relation was. Okay, so give me just a second. Let me stop sharing. I know you get dizzy. Okay, so the recursion relation was here. Okay, so it was 1 over n plus 1 times this sum, right? Okay, that was the recursion relation. Okay, so going back over here. Okay. Now let's see what happens when I run this with 100. It might break on me, but oh. Let me zoom out. So I could do it, but maybe it was just a little exaggerated. All right, so let's go back to doing 10. Which was much better. And you can see that I have the A0 is 0, A1 is 1, A2 is 1, A3 is 5, 6, A4 is 5, 8, A5 is 13 over 50, or 30. Okay, and then here I just have the Taylor polynomial. They do it, it prints it out backwards, but that's fine. Okay, all right, I'll see you in the next problem. If I can get back to zooming. There we go.